Dear colleagues, good afternoon. I am Yuenan Liu, a professor at Renmin University of China. Today, I am honored to present our recent comprehensive study exploring the application of large language models in the detection and protection of personally identifiable information in archival data. My presentation consists of the following 6 parts. Firstly, it's about introduction. In China, numerous archives are under immense pressure to open their collections to the public. Yet they are hindered by a lack of adequate resources to address privacy concerns adequately. Researchers and practitioners have proposed the use of AI to detect personally identifiable information within these vast stores of historical data. However, this approach is commonly beset with obstacles, including a dearth of training data and difficulties in achieving interpretable results. The advent of large language models has illuminated an alternative path, particularly large language model like GPT-4. These models have ushered in a new era of possibilities. Specifically, the ability of GPT-4 to engage in more human-like conversations, including understanding implicit meanings and complex tasks, marks a significant step towards more advanced natural language processing capabilities. On the one hand, large language models are trained on extensive, diverse datasets, developing comprehensive language understanding and even exhibiting emergent phenomena. Thus, they excel in complex tasks through advanced reasoning, generalization, and creativity. Large language models also use transfer learning, applying pre-trained general knowledge to specific tasks, minimizing reliance on domain-specific data. On the other hand, their deep text understanding, enriched by contextual representation and attention mechanism, enhances interpretability. Promising large language models often unsupervised detection of personally identifiable information by passing training material scarcity and boosting interpretability. This study empirically investigates large language models' efficacy in PII detection, aiming to exploit their advanced capabilities in this realm. Secondly, it's about related work. Traditional methods for detecting PII, such as named entity recognition and topic modeling, often fall short when dealing with complex semantic texts. While supervised machine learning has improved the comprehension of context, it relies heavily on fully labeled datasets, which are labor-intensive to create. Moreover, deep learning models, despite their effectiveness in text classification, often operate as black boxes, raising concerns about professional ethics and algorithmic bias in archival contexts. This is where our study introduces a paradigm shift. We embraced the concept of prompt learning, leveraging the few-shot and zero-shot learning capabilities of large language models. This approach significantly reduces the need for extensive training datasets, enabling the large language model to comprehend context and discern hidden patterns, and more importantly, to stimulate human-like reasoning to provide logical explanation for its outcomes. Thirdly, it's about problem and methods. In China, Hangzhou City Archives faces a task of opening about 2 million volumes to the public within 5 years. And the archival records containing personal privacy information cannot be released to the public. The massive review workload, coupled with the lack of well-curated AI training datasets, and the need for adequate interpretability, formed the cornerstone of our challenge. Our solution was to employ an unsupervised large language model, utilizing skillfully designed prompts to guide the model to produce the required output efficiently. This approach not only drastically reduced computational resources and time, but also enhanced the scalability and adaptability of the applications. By designing prompts attuned to personal information cues, the large language model, familiar with various personal data formats, can effectively identify text segments containing such details in large archival records as illustrated in Figure 1. This makes it a powerful tool for detecting personal identifiers like names and addresses. To effectively use large language models for PII detection, we first analyze archival records to identify 6 common personal information categories. Then, using the CRSRF framework, inspired by crisp prompt engineering and comprising capacity and role, statement, reason, and format, we created prompts. In the third step, we enhance large language models with contextual samples within CRSRF, improving their ability to distinguish between PII and non-PII. Next, I will share a specific example. This is a well-constructed prompt following CRSRF framework. The black font defines the capabilities and role. The blue font here is the statement. The red font is the reason. Green fonts are format requirements. This paragraph is the content of the question. And this page is the answer. It identifies the personal names, personal identification codes, and home addresses contained in the previous sentence, and also explains the reason for the answer. Fourthly, it's about data and evaluation. To explore large language models' ability in identifying personal information, we created 3 unique datasets and selected key evaluation metrics. Dataset 1 focuses on names and identification codes with 180 samples. Dataset 2 with 120 samples concentrates on phone, address, and family details. And dataset 3 contains 300 samples that amalgamate the features of both the aforementioned datasets. Aiming for balance, each dataset is split evenly. To ensure reliable personal information detection, avoiding data breaches and inefficiencies, we adopt a set of robust evaluation metrics: accuracy, precision, recall, and F1 score. Our 3 comprehensive datasets, coupled with these metrics, facilitate rigorous testing of our methodologies, fostering systems that effectively safeguard personal data with high reliability and efficacy. Fifthly, there are empirical results and analysis. In order to handle digital records containing PII with utmost confidentiality, this study was conducted within a secure local area network. Therefore, we used the open source ChatGLM2, a bilingual large-scale modeling requiring 8 GB of RAM, compatible with the archival institution's hardware. Notably, the large model operated under a completely unsupervised setting. To assess the effectiveness of the ChatGLM2 model, a baseline model based on BERT was designed. Baseline model fine-tuned on dataset 3, tested on 3-4 PII classification. The training aimed to identify PII in records by using binary classification. The reason we didn't directly use the GPT-4 API is due to the archival environment's network constraints and PII leakage risks. Considering these factors, we used an open-source large language model locally, ensuring data security and net adherence. Our experimental results are summarized in Table 2, where we present the performance of different PII detection approaches across 3 datasets. As shown in Table 2, when employing the CRSRF framework with both LLM dark and LLM scent approaches, we observed a substantial improvement in all metrics. Notably, the F1 score saw a significant increase, with the LLM dark and LLM scent configurations outperforming the supervised BERT fine-tune model in dataset 1. The enhanced performance of the CRSRF enhanced methods can be attributed to the structured prompting, which provided a clearer context for the large language model to identify and rationalize PII presence. This improvement underscores the potential of structured relevance feedback in enhancing the PII detection capabilities of unsupervised models. Our comparative case study not only demonstrates the efficiency of detection models, but also emphasizes the enhanced interpretability and unsupervised nature of an large language model in identifying PII. These characteristics potentially reduce the barrier to entry for deploying advanced PII detection tools in archival systems, promoting both efficiency and adherence to privacy standards. In the conclusion, our research empirically validated large language models' feasibility for PII detection, demonstrating satisfactory performance and potential to match or exceed traditional models. Large language models reduce dependency on extensive labeled datasets and manual feature engineering. Their interpretability fosters trust and insights into decision-making, which makes them user-friendly and comprehensible for archivists. However, our research faced some limitations. The content generated by large language models lacked the rigor of structured data, requiring manual adjustment, and we couldn't use open models like GPT-4 due to data sensitivity. The study's self-constructed datasets lacked scale and diversity, limiting a full assessment of large language models. What's more, hardware constraints prevent supervised fine-tuning for PII tasks. We anticipate that fine-tuned large models would excel, and future research aims to address these challenges. That's all. Thank you very much.